Let's pick up where we left off last time. We introduced these bond line structures. That's how we're going to be drawing our molecules in this class. So I want you to take a minute and convert the following Lewis structures into bond line structures. You're also going to fill in any missing lone pairs or formal charges that should be on these structures. Okay, and real quick, just before we dive in, let me remind everybody what I mean by my bond line structure. That is these little zigzaggy structures here. As we said, each one of these endpoints and intersections in your zigzag represents a carbon atom, and the hydrogen atoms are implied. If there are any heteroatoms, any atoms other than carbon and hydrogen, you have to explicitly draw those in with their chemical symbols in your structures. Okay? Cool. Okay. I'm going to fill in my lone pairs first here, because then we can just make sure that that translates to our bond line structure. What atoms in this here need lone pairs? The halogens, the chlorine, and the bromine, right? Those all live in the same family. That requires 3 lone pairs and just 1 bond. Okay? So what you'll notice about the halogens, because they only like to have that 1 bond, they're kind of like hydrogens, right? They always just decorate the outside of the molecule. They're never going to sit in the middle because they can only have 1 bond. My bromine, same way. 3 lone pairs, 1 bond. Okay? So now if I'm going to do my bond line structure here, I need to draw my little zigzag, right? And I need to know just how many zigs or zags I need. Well, each one of those endpoints and intersections represents a carbon atom. So since I have 5 carbon atoms here, okay, my first line that I draw If I stopped right there, how many carbon atoms did I just draw? Two, right? So your first line segment is 2. Now I'm at 3, 4, 5. Okay, and we can convince ourselves of this, and you'll see me doing this all the time, counting carbons, right? We're just going to count our endpoints and our intersections. 1, 2, 3, 4, 5. Okay, so now I need to put these halogens on there. I don't have to draw in the hydrogens, right? That's the nice part about our bond line structures, is they're implied. But these other heteroatoms here, I do have to explicitly include. Okay, just to kind of make it easier to see why I'm putting them where I'm putting them, I'm going to number these carbons in this chain here. So this we'll call carbon 1, 2, 3, 4, 5. I'm going to do the same thing in my bond line structure. 1, 2, 3, 4, 5. And this is just this simple little trick that's going to help me make sure I put the right thing in the right place, right? That I'm just keeping track of who's who correctly. Okay, so carbon 1 needs to have a chlorine, so I'm going to have to draw in another bond and put that chlorine atom on there. Make sure to include its 3 lone pairs. If I look, carbon 4 is the one that needs my bromine atom. Again, we want these lines to be spaced out as much as possible. We're aiming for 120-degree spacing. So I'm not going to put my new bond pointed down there. I'm not going to bisect that angle. I'm instead going to point it the other direction. That's where my bromine is. Okay. One thing that I'll just note here is you'll see me try to use these best practices in terms of drawing my organic structures. Your homework system is not as picky. Your homework system would let you get away with those ugly structures. One of the things that we're trying to do is do it the correct way here in class, all right? So even though your homework lets you get away with it, let's make sure our notes are nice and pretty so that when we get to the exam, we're drawing our structures correctly. And then I'm done, right? I got all my carbons accounted for, I got all my hydrogens, they're implied, and I have my 2 heteroatoms on there as well. So this would be the bond line structure for that molecule. Okay. If I'm going to do my other example here, which one of these atoms needs lone pairs? The oxygen. And with its 1 bond, how many lone pairs am I going to put in? I got to complete that octet. But unlike my halogens, oxygen doesn't like to have 1 bond and 3 lone pairs, right? So that means when it does, it's going to have a formal charge associated with it. And that formal charge would be -1. All right, so we'll just put a minus sign there. Okay. Again, I'm going to draw my bond line structure. I need to have 3 carbons. So boom, boom. Okay. And again, on this 1, 2, 3rd carbon over here, I'm going to draw that extra bond to my oxygen, and I'm going to make sure to include its 3 lone pairs and its -1 formal charge. All right, so my 3 carbons, 1, 2, 3, plus that oxygen atom. Cool. Okay, what I'd said is I'm not too concerned with you being able to write these condensed structural formulas, but we do want to be able to read them. So just for the sake of completeness, let's put these in our notes, how we would write these. Okay. My first carbon is bound to 2 hydrogens and a chlorine. Okay, I don't have to bother putting that chlorine in parentheses because it's treated a lot like a hydrogen. It just has 1 bond associated with it. And then I'm going to go down the line here, CH2, CH2. Okay, now I'm at this carbon right here. So that has 1 hydrogen and 1 bromine. And then my CH3. Okay, you could have condensed this repeating unit down a little bit further, but you don't really have to. This is perfectly fine. For my other structure here, again, CH3, CH2, CH2O. But I have to be really careful when I'm doing my condensed structural formula because I have to indicate that this oxygen here only has that 1 bond, right? So what we do is we're going to put that formal charge in our condensed structure. That lets me know that when I draw that oxygen, it should have just one bond and 3 lone pairs, right? So those formal charges will appear in your condensed structural formulas. Cool. All right, just so you have all 3 examples here, but now we are going to do an example where I'm going to give you a condensed structural formula and you're going to draw me the bond line structure for that molecule. Okay, so for these here, give me your bond line structure.
Are there other names people use to instead of bond line structure?
Yeah, you'll hear skeletal sometimes. Yeah. I pick one and stick with it. All right, so let's do this first one here. my condensed formula has this repeating unit of CH2s. I can see that because it's in parentheses with that subscript out there. So what are the total number of carbons in that molecule?
8.
8, right? I got my terminal carbon, I got 6 in the middle, and then 1 on the other side. So 2, 3, 4, 5, 6, 7, 8. Okay, and again, we can just count carbons. 1, 2, 3, 4, 5, 6, 7, 8. Always a good double check. Okay. For this one, I'm going to go the long way. I'm going to first turn it into a Lewis structure so that we can see a little bit more clearly what's going on. And then we'll turn that into a bond line structure. If you can do a bond line structure right off the bat, great, right? But if you need to first look at it as its Lewis structure, that's okay. The one thing that's kind of confusing about this is there's a big difference between capital C when it's all by itself and capital CL with the lowercase l, right? Two different elements. One of them would be carbon, the other one's chlorine. We got a lot of C's going on here, right? So we got to read it carefully. In particular, I'm going to color all of my carbons in orange here. Okay, so my carbon backbone is 1, 2, 3, 4 carbons. Now I'll go in and decorate that. That first carbon has 1 hydrogen and 2 chlorines. Doesn't matter which way you put them. If you put the chlorine pointing up, pointing down, to the side, it doesn't matter, as long as you got 2 of them on there. Okay, going down, so that takes care of this one here. Check, check. Going down the line, my next carbon needs 2 hydrogens. My next carbon needs 2 hydrogens. All right, then I have H2OH on that last one. Okay, so I'm going to put my 2 hydrogens on there. So now I have this OH. Importantly, you can't possibly have the H and then the O like this, right? Because hydrogen can't have more than 1 bond. So you're just going to switch those. Oh, you can draw the bond explicitly. If you just said OH, that was fine as well. Okay. We sort of mentioned, and we'll talk a little bit later today, we'll see these OHs a lot because these represent a very popular functional group in organic chemistry, what are called alcohols. So when you see that OH in your formula, that's an indicate you're going to have that OH group in your molecule. And then to be good, I'm going to finish this off by putting those 2 lone pairs on my oxygen atom. What's up?
So do you prefer us to just start getting used to drawing it just OH without the little dash?
It doesn't matter. I mean, it's extra writing to put in the little dash, right? What you'll see is that when we talk about reactions that use that OH bond, we'll show the bond. And if we're not talking about that bond, then we'll just kind of write it a little bit more in a shorthand. Either one are perfectly acceptable. Okay, so now that we have our Lewis structure and we can see our layout of our molecule, it's a little bit easier to turn it into that bond line structure. We have 1, 2, 3, 4 carbons. So I'm going to draw my zigzag line with 4 carbons. 1, 2, 3, 4. So there's my carbon backbone there. Again, we can make it sort of easier to see what's going on here by numbering those carbons. Carbon 1 needs 2 chlorines, right? So I got to draw both of those bonds. And so if we're being good and spacing them out, it'll look kind of like a Mercedes symbol there. Chlorine, chlorine, with its 3 lone pairs. All right, and then lastly, we're going to put that alcohol group onto that 4th carbon. And again, we can draw it in its more condensed form, just OH. Okay, so there's my bond line structure given those condensed structures. All right, again, if you need to sort of, when you're starting out, go through your Lewis structure so you can better get a sense of how things are bonded, that's not a bad strategy. All right, but again, drawing our zigzaggy lines, and we're counting our carbons, and then decorating them accordingly. Okay, we saw an example of this, but let's just kind of lay out all of our examples here. And that is our formal charges. We looked at those in Lewis structures. Now look at those in bond line structures. All right, so what I'm going to do is I'm going to draw a bunch of bond line structures, and you're going to draw in any missing lone pairs and formal charges based on the rules that we laid out. Oh, ignore that.
So we're filling in the lone pairs?
Lone pairs and formal charges, yep.
For the last one, I mean, they're just kind of the same as if it was like diagonally, right? That line, but just the carbon.
Yes, and so this is how as soon as we put 4 bonds on there, then we have to space them out 90 degrees. So you'll only see that if you have 4 bonds explicitly drawn, but yes, that's kind of the only way that we deviate from that 120 rule.
So if he's missing a bond, does that assume that it has a lone pair?
Correct. If you don't see a bond explicitly drawn, there's no bond there, right? So then you're filling in the correct number of lone pairs to give it its full octet. Otherwise, you're changing the number of atoms that are on this molecule, right? I gave you the molecule with its correct number of atoms already. All right, and then the other thing that we're going to do after this, so you can get a head start if you're already started, is we're going to do the chemical formula of each of these as well. Make sure that we're spying the correct number of carbons and hydrogens and heteroatoms.
atomic order the hydrogen's always second? Or
In your molecular formula, in your chemical formula? No.
This is kind of from yesterday's. So we had went over this one. We ended off on this one. I just was kind of, because I didn't really understand it. I just wanted to kind of confirm with you if that makes.
That would work. This is kind of an example of one that's a little bit too much of a pain in the butt to do in the condensed way. Yeah, that would work though.
Okay.
Yep. One of the things that makes the condensed tough is that there's no one right way to do it. There's several times multiple ways to draw the same molecule. All right, let's do a few of these together to make sure we're on the right track, and then I'll give you some more time to finish it up here, all right? So, first thing I want to do is fill in my missing lone pairs here, all right? What needs lone pairs in this structure? The oxygen. Oxygen's got lone pairs on it, and in this case, it's only got one bond, so how many lone pairs do I need to complete that octet? 3. And when oxygen has 3 bonds and 3 lone pairs, its formal charge? Negative. All right, more lone pairs is more negative charge because those electrons are negatively charged. All right. Similarly, if I go over here, now I have nitrogen. How many bonds does this nitrogen have? 3. It's got these 2 hydrogens because it's a heteroatom. I got to draw my hydrogens that are attached to the nitrogen specifically. And it's got this carbon atom over here. So it's got its 3 bonds. It's nice and happy. It just needs 1 lone pair. And so the formal charge in this structure would be what? 0, right? Because nitrogen's happy. It's got its 3 bonds and its 1 lone pair. Okay? Okay, so now let's jump back over here and do our chemical formula here. So C something, H something, O something. That's what we're trying to put in. And the permutation here, if you put hydrogens first or the oxygen first, it doesn't matter. There's, strictly speaking, no standardized rule for writing your molecular formulas. Generally speaking, in organic chemistry, we will start with carbon because, you know, it's carbon, it's the star of the show, but there's no wrong way to do it necessarily. Okay? So how many carbon atoms do I see in this structure? 4. I got my endpoints and my intersections here. So these are my 4 carbon atoms. Let's do hydrogens last. They're the toughest. All right? How many oxygen atoms do we have in this structure? Just one. And I know that there's just one because I have to draw the symbol if it's in there, and there's just the one O. Okay?
The negative would drop right onto the.
Yeah, absolutely. We definitely have to include that formal charge in our formula as well. So we're going to put that minus sign there. All right, and now we're going to do our number of hydrogens. So we're just going to look at each carbon and we're going to fill in so that it has a total of 4 bonds. Right? So this carbon at the end will need 1, 2, 3. What about this one right here? Just one, right? It's got 1 bond to oxygen, then 2 carbons on either side, so it just needs 1 more, that hydrogen. So that's 4, 5, 6, 7, 8, 9 hydrogens total for that structure, right? Remember, for your hydrogens, they are implied. You're just going to fill them in so that every carbon is happy. Every carbon has its 4 bonds. Let's play the same game over here. How many carbon atoms do we see?
3.
Just 3. C3, H, whatever. We'll save this one. And then my N, I just have 1. I don't have any formal charge, so I'm not going to draw any charge in this formula here. When I go and I count my hydrogens, again, I need to fill in for each carbon. 1, 2, 3, 4, 5, 6, 7. And am I missing any? Yeah. All right. Don't forget these that we wrote in here. So 8, 9 hydrogens total. Cool. All right. So that's the name of the game here. Okay. Take a second, see if you can't finish off with our other examples. I tried to do an example of each formal charge state for oxygen and nitrogen, right? We got one of each example up here. Positive, negative, and neutral. I'm filling in lone pairs here. How many do I need to put down? 2. My oxygen currently has 2 bonds, right? These 2 sticks represent a double bond. So that's 2 bonds. It needs its 2 lone pairs. So what's its formal charge here? 0, right? This is a happy oxygen. How many carbon atoms do we have? 3. 1, 2, 3. So we do our formula. We got C3. We'll fill in the hydrogens. O. How many hydrogens do we see here? So this is 6. This is a tricky one here, okay? The endpoints, I think, are pretty easy to see. We come up with these what are called terminal carbons, the one on the very end of the molecule. We've dealt with these a lot. They always will need those 3 hydrogens. But that's it. Those are all the hydrogens. If we look at this middle carbon here, it's really tempting to try to stick a hydrogen on there. But we already have our total of 1, 2, 3, 4 bonds associated with that carbon, right? Don't forget that double bond counts as 2 covalent bonds. So there won't be any hydrogens on that middle carbon, so a total of 6. Okay? We will work with double bonds kind of a lot, so we'll get this sort of practice down. All right? In fact, this molecule in particular plays a little bit of an outsized role in organic chemistry. It's really important. We use it a ton to just even clean our glassware, and y'all might have a little bit of a relationship with it. I don't know how to say it as well. You might know it as well, especially if you use nail polish. This is acetone here, okay? So just a very common organic molecule that you will see very often, acetone. You don't really have to know that yet, just fun fact, all right? But yes. When we come across some popular ones, I'll try to point them out here. Okay. So now I also have a carbon-oxygen double bond, but I now have an additional hydrogen over here. So how many lone pairs am I going to fill in? Just 1, right? An oxygen with 3 bonds can only then have 1 lone pair. And so that is how we would draw an oxygen with a formal charge of +1. Oxygen, super pissed off to have this +1 formal charge, but we do see it, especially as just a very short-lived intermediate in a chemical reaction. So, well, like we said, these formal charges, they're not the most stable states of these molecules, but oftentimes in a chemical reaction, you have to go through some sort of unstable state in order for the chemical reaction to occur. 2 very stable molecules aren't really going to react with one another, right? So these formal charges play an important role when we start talking about reactions. Okay, so we got our lone pairs, we got our formal charges. How many carbons do we have in this molecule? Just 2. 1, 2. And we have our 1 oxygen and its +1 formal charge. We're going to include that formal charge in that formula. Okay, so now I got to fill in hydrogens. Again, this one's a little bit of a challenge. We got our terminal carbon, which will have 3. And what about this one here? How many bonds do I already have? 3. So there's just 1 hydrogen on that carbon. So that's 4 plus my explicitly drawn 1 over here brings me to 5. Okay. All right, so this one, I'm going to look at my nitrogen, my heteroatom, and I got to figure out how many lone pairs to put down. It's got 2 bonds, so how many lone pairs? Got to fill in that total of 8, right? So it needs 2. We said nitrogen likes to have 3 bonds in 1 lone pair, so if it has 2 bonds and 2 lone pairs, that means it's got a formal charge of -1. Okay, put that minus sign on there. When I'm counting carbons, remember all your endpoints and intersections. So that means this little random stick over here indicates that there's a carbon on the other end of that oxygen. Not an oxygen, other end of that nitrogen. Okay, so then I'm going to fill in my hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So in my formula, I got C3H8N, and what am I going to make sure to include? That negative charge. Cool. All right. So then last one, now I have nitrogen. It's got 4 bonds, so how many lone pairs am I going to fill in?
2.
None, and it's already got its complete octet. And so if it's got 4 bonds and no lone pairs, that's how we draw nitrogen with a formal charge of +1. I could have drawn this more condensed by just saying NH3. That's perfectly fine as well. You actually would probably see it like that more often, but just to sort of draw out these bonds so we can see clearly. Yeah, let me just get rid of this so we're not confusing. All right, cool. So then how many carbons do I have? Just 1. And how many how many hydrogens are on that carbon? 3. So I have a total of 6 in the molecule, but there are 3 on that carbon. All right, you're always just kind of filling in with your mind's eye to give carbon those 4 bonds. So C1, so I guess I just write C, H6, N with that plus sign. Cool. All right, so all these little markings, all these little dots I put in for my carbons and all of those hydrogens that I drew in, this is what we're kind of training to do, is to be able to look at those bond line structures and fill in that information with our mind's eye, right? Being able to see where those hydrogens live in that molecule. What's up?
So typically in a condensed formula like that, would you include the formal charge?
So always have to include the formal charge in either a condensed or a chemical formula. This would be just a chemical formula because I didn't write down how it was connected. I just smushed everything together, right? And really my purpose in doing this is just so we make sure that we can see how many hydrogens and carbons there are in these structures. That was my goal. Okay, cool. So now that we know how to read our bond line structure, we're going to talk about something called the classification of carbons. Okay, so when we look at a bond line structure, we give the carbons in that structure a classification based on how many carbon neighbors they have. Okay, so what I mean by classification is the number of carbon neighbors. All right, so I'm going to do an example structure here. The carbons that are at these endpoints here, they only have one other carbon neighbor. They're both bound to just this guy in the middle here. These are what we would call primary carbons. We use this 1 degree symbol to mean primary. And that means those carbons have just one carbon neighbor. So again, both of those carbons that I colored in orange there, they are both primary carbons in that structure because they're each bound to just one other carbon atom. The carbon in the middle is not a primary carbon. It's got a carbon on either side of it. So this is what we would call a secondary carbon. So within this same structure here, the middle guy is a secondary carbon. It's got 2 carbon neighbors. Okay, so now I'm going to draw a new structure here where this middle carbon is bound to 3 other carbon atoms. This is what we would call a tertiary carbon. Again, we use that 3 degree symbol. It's got 3 carbon neighbors. Okay? Just for the sake of practice here, the one in the middle is a tertiary carbon. What are the other 3 carbons in this molecule? Primary, right? They're all just bound to that one carbon in the middle. Cool. Okay? And then we can even have what's called a quaternary carbon. Okay? Now, since this carbon is going to be bound to 4 other carbon atoms, we can't space it out 120 degrees. So this will be where you see us drawing our bonds at a 90-degree angle. So this plus sign here, first of all, let's just apply our bond line rules here. How many carbons do I see in this plus sign?
4.
So we got each endpoint, 1, 2, 3, 4, and that intersection in the middle. So we got a total of 5 carbons here. The one in the middle, bound to those 4 other carbon atoms, would be the quaternary carbon in this structure. Okay, so this is kind of just this like tool we're going to add to our toolbox here is the classification of carbons. For right now, we're just practicing being able to see what, this carbon is a quaternary, this carbon's a primary, etc. The reason that this is important is because when we talk about chemical reactions, we'll find that quaternary carbons don't behave the same as primary carbons, right? So it's just kind of building this language to be able to go forth and talk about chemical reactions with, all right? But right now, we're just worried about the classification process. How many of each do we see, okay? So I'm going to write down this big, ugly molecule here. And you're going to find all the primary, secondary, tertiary, and quaternary carbons in that structure, all right? We're going to classify all of our carbons according to this scheme here. Right? So to be clear, every carbon in this molecule gets a classification. It's not like you look at the molecule and the molecule as a whole gets a classification. It's each atom within the molecule, right? So within this molecule, how many primary carbons do we have? So we got on these endpoints here, this has one neighbor, 2, 3, 4, 5. These are all primary carbons. I'm going to do my primary carbons in orange, kind of be consistent with up here. What about secondary carbons? How many secondary carbons? 2. We got this one here, and and this one here. Those are all my secondary. Do we have any tertiary carbons? Yes, we have one right here. And lastly, what about our quaternary carbons? Just one right there, middle of the plus sign. Okay, and again, you'll just notice sort of with my good organic chemistry structure drawing, I did everything with that little zigzaggy 120 degrees spaced apart until I got to this quaternary carbon where I was forced to close that bond angle to be 90 degrees instead. Okay. Cool. All right, that's all pretty straightforward. Hopefully you'll practice that with your homework, so I think we'll get that down. Again, we'll need that language when we go into the next chapter and start talking about our reactions. All right? And our first step is going to be talking about reactions of alkanes. So what the heck does that mean? All right? In organic chemistry, we sort of divide up molecules based on what are called the functional groups that molecules contain. Some patterns that we see in the atoms that it contains, the bonds that it contains, okay? And so we're going to sort of lay out our functional groups that we're going to be discussing this semester. Okay, so given an organic molecule, we throw it into one of these functional group bins, and everything within that bin behaves very similarly from a chemical standpoint. All right, and so our first step is sort of the easiest of the organic molecules, what are called alkanes. An alkane consists only of carbons and hydrogens and has all single bonds. Right, so just an example of an alkane would be one of our just zigzaggy lines without any heteroatoms or any double bonds in there, right? All single bonds, only carbons and hydrogens. Those are what our alkanes are. All right, so fun fact, alkanes are the fuel that we use a lot. Gasoline is a mixture of a bunch of different alkanes. Propane that powers a grill is an alkane. These are these molecules that as human beings we've kind of gotten addicted to combusting to use as energy, because it turns out that when you take these and you burn them, you combust them, it releases a crap ton of energy, right? And that's why we've sort of gotten addicted to them to power the lights around us and all that sort of stuff. Unfortunately, when you do so, you always create carbon dioxide in the process, which is now why we have this sort of climate crisis on our hands, is because we were burning a whole bunch of these alkanes and creating a whole bunch of CO2, all right? But the gasoline that you put in your car is just a mixture of a bunch of different alkanes. You see on that little rating, it's got an octane rating. That's one of the particular alkanes that are in that mixture. Just fun fact. Okay. Also turns out that aside from combustion, they don't really have very many reactions. They're kind of a boring functional group. Okay, so the next one that we're going to learn, which is way more interesting, are what are called alkenes. All I did was change that ANE ending to an ENE ending. These also contain only carbons and hydrogens, but have at least one carbon-carbon double bond. Right, so if I took my alkane structure and I just drew in one additional carbon-carbon bond, that would be an alkene. All right, what we're going to learn is single bonds, kind of hard to break. This double bond, way easier to break. So these molecules are much more reactive. All right, and then lastly, we have an alkyne, a YNE ending. What do we think is going to be in our alkynes? A triple bond, right? So these are now only carbons and hydrogens, but they consist of one carbon-carbon triple bond. Then it's a mixture of both, and we're not going to mess with that. Yeah, you can definitely have more than one functional group within a molecule. You're getting way complicated at that point. We don't have a special name for that, basically. Importantly, when we draw our alkynes, the carbon with that triple bond has a linear geometry. All right, so what do I mean by that? Let's say we're drawing our carbon backbone here. We're doing our zigzaggy lines. All right, but now I'm trying to put in a triple bond on this fifth carbon here. You're not allowed to draw it kinked upright like this. That's not the correct geometry of that carbon. It has to be drawn in a straight line. So one more going down.
We would automatically assume there's a carbon in between.
Yeah, so exactly. And I was just about to point this out because this is the easiest carbon to mix when you're counting. Importantly, there is a carbon located right here at the base of this triple bond. We're going to say, don't forget about this carbon. Okay, and sort of the whole logic, but like, why am I making you draw these things with certain spacing and all that jazz? It's important to remember that molecules are not 2D flat things, right? They are three-dimensional objects that have this three-dimensional geometry. When we draw it on the page, we try to do our best to represent that geometry with this flat structure that we're drawing. We're not going to sort of be able to draw in 3D. That's not something that we can do, right? But instead, we try to best represent the correct structure of that molecule on this 2D plane here. All right, so again, that bond, if you built that molecule with your model kit, you would see it has that linear geometry. That's what all triple bonds do. You can't draw it any other way, or you can't build it any other way. So that's why we draw it on paper to represent that same thing. Okay, so these are our three functional groups that contain only carbons and hydrogens, right? They don't have any heteroatoms in there. An alkane is all single bonds. An alkene means that you've thrown a double bond in there, and an alkyne means that you've thrown a triple bond in there. All right, so now let's get to some of our heteroatom functional groups. We sort of already mentioned this one a few times. Alcohols. These contain an OH group, which is what's called a hydroxyl group. Sometimes we get lazy and just refer to it as an alcohol group, but technically speaking, it's a hydroxyl group. So any molecule with that OH bond in there would be considered an alcohol, any organic molecule. Okay, so I could stick it at the end of the molecule. I could stick it in the very middle of the molecule. Doesn't matter. These would both be classified as alcohols because they both contain that OH hydroxyl group. Okay, you would have learned in Chem 1B that hydroxyl group is capable of hydrogen bonding. So these are one of the more polar organic compounds that we will work with. And that's typically what they're used for in the lab, is as a polar or polar-ish solvent. Okay, so you come come across alcohols quite a lot. This one right here is actually isopropyl alcohol. I feel like it's not really as popular anymore, but you always used to have this in your first aid kit to clean wounds with. It hurts like hell. I guess that's why they replaced it. So that's what happens when that oxygen is kind of at the end of the molecule. It needs those two bonds, so it's got a hydrogen. If we put the oxygen in the middle of a molecule, it's no longer considered an alcohol. It's considered what's called an ether. These contain oxygen sandwiched between two carbons. All right, so for example, we have an oxygen and it's flanked by two different carbon atoms. I guess we should be good here. How many lone pairs should I be putting on these oxygens? Two. Okay. The next three functional groups, they all contain the same bond that's very important in organic chemistry, so important that the bond itself gets a special name. Okay, so we have a special bond we're going to learn about, what's called a carbonyl bond, and this is a carbon-oxygen double bond. So we did that molecule acetone earlier. All right. Acetone contains this carbonyl bond right here. That is what the name of the bond itself is. Okay, and so importantly, when we get to these functional groups, you're going to hear me say over and over again, I'm going to refer to the carbonyl carbon. That's the one at the base of that double bond. Or the carbonyl oxygen. That's the oxygen in that carbon-oxygen double bond. All right, so again, these functional groups contain a carbonyl bond here. Okay. We have ketones and aldehydes, and these are both very similar. Let me just do an example. Okay, acetone would be an example of a ketone. All right, but if instead I drew those three carbons and I stuck that carbonyl group on the end, that would be considered an aldehyde. It is so annoying that these are classified as different functional groups because they behave the exact frickin' same for the most part from a chemical standpoint. They both have that same carbonyl bond, which really informs the chemistry of these molecules. There's a very important historical reason that they're different, and that's because sugars contain either a ketone or an aldehyde. Sugar chemistry is some of the earliest chemistry, and that's kind of how they first divvied up these different classes of sugars. And that just kind of persisted forever as these two different functional groups. We'll study them lumped together because, again, they behave very, very similar. A ketone is simply when the carbonyl is in the middle of the molecule and an aldehyde is when you have that carbonyl bond on a terminal carbon. Right, sticking off on the end of the molecule. I don't know what they're doing up there.
I see a lot of chairs in the
Okay, the next one is what's called a carboxylic acid. These contain a carbonyl group, but they also have a hydroxyl group bound to that carbonyl carbon. So here's my carbonyl group here, but what makes a carboxylic acid special is it's got also that OH group bound to that same carbon. Okay, as the name implies, these groups are acidic, right? It's a carboxylic acid group. In particular, it's this hydrogen right here that is very easy to remove. That's the feature of an acid. It's got a donatable hydrogen, a donatable proton, right? That's this guy right here. This is my acidic hydrogen. The last one that we're going to talk about are amines. These are the functional groups that contain nitrogen. All right, so we had a whole bunch of different classifications for these oxygen groups. Anything that contains nitrogen, we kind of just lump into the same category. And so for an example, we could have just a nitrogen sticking off the end of the molecule, or it could be in the very middle of a molecule. Right? With oxygen, we classified these as two different functional groups. For nitrogen, we throw them in the same bin. Anything you see with the nitrogen in there is classified as an amine. Okay? So these are going to be our functional groups that we discussed this semester, all right? And so for right now, we just need to be able to spy those patterns, right? If we see an OH group, we say, ah, yes, this is an alcohol. When we see just that zigzaggy line with all single bonds, that's just an alkane, right? So we just need to spy these patterns here, okay? So again, we have our only carbon and hydrogen functional groups, alkanes, alkenes, and alkynes. We have a bunch that contain oxygens. Alcohols and ethers will contain single bonded oxygens. Alcohols, it's at the end of the molecule. On ether, it's sitting in the middle. And then we have a bunch that contain this special carbonyl bond here, this carbon-oxygen double bond that we're going to see quite often. Ketones and aldehydes both contain that carbonyl group. For a ketone, it's in the middle of a molecule, whereas aldehydes, it's sticking off at the end of the molecule. And then a carboxylic acid contains both that carbonyl group and that hydroxyl group, right? The carbonyl group of a ketone or aldehyde, but also the alcohol's hydroxyl group, all in sort of one shot here. And again, the whole shtick is that these play the role of acids. They can donate that proton. And then lastly, when we have nitrogen, we call those amines. Any group molecule that you see with a nitrogen in it would be classified as an amine. Cool, that's all I got for y'all.